Hey everyone, how are you? Good to see you all again. Let's continue doing some stuff with generating functions and with recursions and so on. So I want to continue from where we left off last time because that will give us a kickoff point for a general solution, which is what we want to do today. So we're now going to move into how you solve every single homogeneous linear recursion, recurrence, whichever word we should use. And it's inspired by this key observation, which we did last time, where this is the problem we ended with. We were doing something with like an equals 6, an minus 1 minus 9, an minus 2. And when you did the generating function stuff, you found out that the denominator you got had a perfect square. So it wasn't actually partial fractionsable. In fact, well, it was. The way you do partial fractions in calculus class is that if you have a repeated root, you go and use that particular type of term to the power however many times it's repeated. Okay, so we got this, and after we got this, we said, well, we don't want to take Taylor series, we don't want to take derivatives, but we actually sort of do want to take derivatives in a different way. It's not like we want to take the Taylor series type derivatives, but the key idea was that if you're over here, you can actually go and solve the problem by just taking the derivative of something. Chris, you have a question?
Instead of keeping the square on the bottom, if we FOIL out the square and then it's like 1 minus 60 plus 9z squared, could we use minus 60 or 60 plus 9z squared as its own thing and just do it that way?
Oh, yeah. Okay, so there's a lot of different ways you can do this. Okay, so that was an interesting question. The question was like, hey, this is also a geometric series, isn't it? So I could actually, so let me just do it right under here. I have the old notes just right here, so we can say, well, this also happens to be, if I took z, that just shifts everything. Actually, when you multiply by z, as we've seen elsewhere, all you do is you just kind of shift what power of z the coefficient is next to. But then you're saying, let's just call this a big geometric series. 1 plus 6z minus 9z squared, okay? And the next term would be plus 6z minus 9z squared plus ... So this is also true. You could do this. The only problem is I don't know how to make it nice. But by the way, I'm glad you said that, because we're going to see something else today where it's something like what you're suggesting. There are many different ways to go and get... is it like there are many different ways to skin a cat? Why would anyone want to skin a cat? Anyway, I just don't understand that one. I was going to say there's many different ways to it, but I was like, the English way to finish this is something that I don't imagine we would ever want to do. Let's not think about that. So like, if we just keep going on here, you get all these powers, and I don't know what to do with the powers because they get too big. But we'll see another example soon, which uses a similar way of looking at things differently. Thanks for asking the question though, Chris, because that's starting the next one of the things we'll do today. Continuing on to this, we were like, okay, well, maybe I can recognize it as some kind of, I took, this particular geometric series and take a derivative of it. Maybe the cat is climbing all over you. Yeah, I don't know. I still don't think we should skin the cat, but let's keep going. So I guess I don't see any circumstances for skinning a cat. But let's keep going. And it's like you take a derivative, and what I wanted to get to was there's an interesting punchline where the coefficient of z to the power n was this like n plus 1 times 3 to the power n plus 1, which we kind of simplified down, and we saw, oh, well, I could think of it as the coefficient of the an, which is the coefficient of z to the n, was just n times 3 to the power n minus 1. So that's interesting because that's not a pure exponential. In the previous things, whenever we had these distinct roots for the characteristic polynomial, we just had pure exponentials. Now we have an exponential, which is also multiplied by an n. Let's see what happens if we take this to some more further steps to see how you'd solve this. This is just some, checking that the thing worked. That was what we did. We found out that the thing worked. I need to skip past this. This was like people who stay after the class always ask random questions, and we just answer random questions. But let's continue on here. Like suppose I have some general other recurrence, right? Let's suppose I have a general recurrence of the form an equals, we'll give it an capital A, an minus 1 plus capital B, an minus 2 plus capital C, an minus 3, okay? Actually, let's put a fourth one. I want the fourth one just so I can prove a point. Plus capital D, a sub n minus 4, All right. So now I've got a bunch of these. Now, how do you do this? Let's just do the generating functions exercise. But we're not going to do everything in super detail because we've done this a bunch of times before, even with numbers. So what you do is you just let your generating function, f of z, be a0 plus a1z plus a2z squared plus a3z cubed plus, and onwards. As we've seen many times before, what you do is you'll break this apart. Oh, actually, those 4 terms have to stay there because I can't break any of them apart. The breaking apart only comes from then onward, right? But what you end up getting is let's use some blob math because I'm tired of writing subscripts. I'm going to say it's a blob plus a blob z plus a blob z squared plus a blob z cubed. I will write blobs whenever I really don't care. What they are, we'll figure it out later. And then you get this big brace which opens up. And this is where I usually make some mistake as I'm writing things down. But the A4 is the first one that breaks apart. And A4, how many A0s does it have? It's going to have D A0s. So it will be D, capital A0, Z to the 4th. Okay, but then that's going to add together with a bunch of different things, plus C a sub 1 z cubed plus B a sub 2 z squared, and then plus C a sub 3 z cubed. What did I just do? No, those powers of z are all wrong, So those are all z to the 4th. Sorry, guys. Because this should be the z to the 4th term. It's very hard for me to count. Yeah, thanks, guys. Yes, Abby, thank you very much for correcting. It is z to the 4th throughout. Thank you so much.
Coefficient be a instead of c.
It should, yeah, thank you. Okay. Thank you. We're good now. Okay, so thank you very much. This should be like whatever those coefficients are, keeping track of the indices is tough. Good. And then it continues. I'm going to just write plus dot dot dots because we know it's going to be these things. I did not screw up on the plus dot dot dots. This is why I like to do math with dots and blobs. Actually, that's why I'm a theorist. Okay. Good, we got this. Now the next thing is we need to recognize all of these as some kind of things about f. So, can someone help me with the first row? And it's okay if your expression has blobs in it. What's the first row? Okay, Aaron?
Would it be f of z times d times z4?
I think you're right. I actually usually forget the d, but I think you're right. It's going to be it's got all those d's inside, and yeah, I have to put an extra z to the 4th. Okay. Next one, the yellow thing. Anyone want to help me with that one? Blobs are okay. Brayden.
That'd be f of z times c z cubed minus some blob.
Is it just a blob?
It should just be a blob because it's a blob z cubed.
Yeah, blob z cubed. Okay, remember blob is just like blob is like square root 2 or something. Okay, good. Blob, by the way, can depend on the capital A, the capital B, the capital C, and the capital D. Next. Anyone want to give me this one? I'll just do it. Okay, I'll just do it. I think people get the sense of what to do here. This is f of z times, except when I do it, I probably make a mistake. But anyway, I think it's this one. It's bz squared. And then we have some blob stuff, right? So I'm getting kind of tired of writing these blobs. So important thing here is I'll have a blob, what is it? I'll have a blob z to the power, oh boy. What is the blob stuff? Well, I have an a0 and an a1 term, right? And trying to think, what is the easiest way to do this? Yeah, actually, I do want somebody else helping out here because I want to make sure that everyone's on the same page of how much blob stuff to have. And if it's easier for you not to use blobs but to use a sub things, that's also okay. Can anyone else give me this? Because I just want to say there's like one step here where you saw even I paused. And I've taught this class a bunch of times, so I want to make sure everyone else is with me on this. It's not just one blob thing. Jack.
Yeah, I think so. There's one blob that's the z term, and then there's another, and then another that's the constant term.
Is that right? So I'm looking at this and I'm like, you know what? Let's not use blobs because I think the blobs are getting things more confusing at this stage. Can we give an exact blob for the z? What is the one with?
Shoot, is that BA1 z?
Okay. So let's see. That's why I'm doing this. That's why I'm doing this. Because as you saw, I paused also. So first, let's look at that BA1Z. Is that actually what's missing? Wait, there's an F. Do we need... Wait, no, F. Just a second. What's missing here? I see that somebody else raised a hand. So we got lots of people raising hands. Because we're all trying to figure out this off by one thing. Andres.
So I think it would be BA1Z cubed, right?
Yeah.
F of z, b z squared.
Right.
A1 term would be BA1Z cubed.
Okay. And what else do I have?
And then B a sub 0 z squared.
Okay, yes, and indeed the blobs are more confusing here. And the reason is because, you know, like, as I was looking at this guy, I was like, okay, well, if BA2Z to the fourth is the first term, I'm a pattern guy. I was just thinking to myself, what's next? The next thing was BA3Z to the fifth, right? That was the next thing that I had. And so I was like, what's missing? The missing stuff is the A1 and the A0 term, right? So if I want to subtract out the missing stuff, I have to write down, what is the A1 term? Well, that's whatever is like before this one, which is BA1Z cubed. And what is the A0 term? It's even before that. So every time I kind of drop an index on the A, and I lose a power of the Z. Okay, so I think that's that one. And we would blobify it soon. Okay? And the last one, this pink thing, I'll say it's f of z times capital A times z. Okay. And how much blob stuff or how much stuff do we subtract off? Can someone help me with that? Actually, Lingray, I know you raised your hand for the previous one. Do you want to do this one?
Yeah, sure. I think it's. Do you want a blob thing?
Let's use the full A stuff. Let's use the capital A stuff.
Sure. I think it's minus A times A2 z cubed. Minus A times A1 z squared. And minus A naught times c.
Okay. And if we look at this, we are indeed just like pulling back the previous ones. Every time we just like make the A sub something, the sub something goes down, and then the power of z goes down, and then that way we go all the way down to the A naught, to the A0. So this is good. So I think this is all correct. And we've got some expression for f of z. Great. And now we've got all of these stuff with these blobs, with these capital A's, these little a's. And we're getting kind of tired of seeing, like, this is a big, long thing with some blob z cubed minus a blob z squared minus a blob z. Well, what I'm going to say is that's actually a polynomial of degree 3 in z. Okay, so this is a polynomial of degree 3 in z. Actually, over here in the blue, that's also a polynomial of degree 3 in z. Up here, this is a polynomial of degree 3. The yellow one is a polynomial of degree 3 in z. And all of these blobs I wrote in front, that's a polynomial of degree 3 in z. So my claim is, if you shoved all the f's to one side, I would end up by seeing that if I factored, I would get 1 minus capital A, capital A z minus capital B z squared minus capital C z cubed minus capital D z to the fourth times f of z equals, what would be left over? What's the form of the right-hand side after I've shoved all my f's over to the left? And what kind of stuff does the right-hand side look like? Braden.
It's going to be blob plus blob z plus blob z squared plus blob z cubed, subcubic.
Yep, some cubic. And the important thing is blob means like some number depending on capital A, capital B, capital C, capital D, and it doesn't involve n. It also doesn't involve z. So remember, blob equals depend on capital A, capital B, capital C, capital D, but not n and z. Okay? So we've got this, and that means now I can write down what is f of z. Just divide through by this this thing I'm multiplying f of z by, and I get that f of z is equal to some polynomial of degree 4, blob plus blob z plus blob z squared plus blob z cubed, over this 1 minus capital A z minus capital B z squared minus capital C z cubed minus capital D z to the 4th. Okay, and now it's time for partial fractions, right? I'm just showing you how, again, this 1 minus capital A minus 1 minus capital AZ minus capital BZ squared, and all of this, that whole thing shows up again. And I'll say last time we did some trick about like the 1 over z's. I won't do that again, but I'll say that if you could solve for the 4 different roots of this, you'd be able to, if 4 roots of this, if they were all different, you'd be able to partial fractions this thing. So the game then becomes, hey, can we find a general formula for f of z? General formula for the coefficients of f of z. How do I find a general formula for the power series of, we have this f of z is equal to some polynomial of degree 3, blob plus blob z plus blob z squared plus blob z cubed, divided by 1 minus capital AZ minus capital B z squared minus capital C z cubed minus capital D z to the 4th. Okay, and so step 1 is to attempt to solve for the roots of some equation. What we saw last time, let me write a J which is more clear. What we saw last time is just find the roots of this equation. There was an equation which was lambda to the 4th minus a lambda cubed minus b lambda squared minus c lambda minus d. Okay, and I'll say if you're curious again, how do I get to flip from this like 1 minus thing into this lambda to the 4th minus thing? There was this 1 over z trick, which if you do from the previous thing, look at the previous thing, you'll also get again. And if you found these roots, we got some lambda 1, lambda 2, lambda 3, and lambda 4. Lambda 1, lambda 2, lambda 3, and lambda 4. We already know that if they're all distinct, you're really happy. Okay? So we know from before, from the linear algebra thing, but also from this whole study, we know that if lambda 1, lambda 2, lambda 3, lambda 4 are all distinct, then you're able to go and write your f of z as this like nice partial fractions. F of z is equal to, it will be like something, some alpha over 1 minus lambda 1z plus some beta over 1 minus lambda 2z plus some gamma over 1 minus lambda 3z plus some delta over 1 minus lambda 4z. And by comparing coefficients, just like we did before, you would know that the coefficient of a sub n was like some combination of these powers of lambdas. Okay, so just like before, comparing coefficients implies that a sub n is equal to alpha times lambda 1 to the n plus beta lambda 2 to the n plus gamma lambda 3 to the n plus delta lambda 4 to the n. And you'd finish that way. But now the problem is, what if it isn't? Okay? And I chose a 4th degree because I want to do something with like, I need enough space. I need 4 different factors for this. Okay? So the next thing I want to do is I want to put a numerical example of what would I do in the following situation. Okay? So this is great if they're all distinct. But what if they're not? But what if this like lambda polynomial, lambda to the fourth, minus a lambda cubed minus b lambda squared minus c lambda minus d, what if that's equal to lambda minus 7 cubed times, I don't know, lambda plus 2 to the 1? 2 is unfortunately a bad choice. Let's choose another random number like 5. Okay. 2 looks too small. You might find some pattern and think that there's a pattern. But remember, 7's the magic number. So suppose I got this thing. Now, what would you do? Well, if you end up with this, actually the partial fractions thing, it would tell you by the same thing as the partial fractions, it's the same 1 over z thing, which we saw last time. The 1 over z thing will tell you that the f of z is equal to, it's like a polynomial of degree 4, blob plus blob z plus blob z squared plus blob z cubed divided by, and this would become 1 minus 7z cubed times 1 plus 5z, 1 plus 5z to the power 1. Okay, so this is this 1 over z thing. That's like I flipped somehow from the lambda thing to the z stuff, and effectively all that happened is you divide both sides by z to the fourth or something, and you get it. So I want to say, suppose we got to this point, which is where we found out that we solved this thing, and so the lambdas are 7, 7, 7, and negative 5. Oh no, what do you do with 3 7s? Well, we need to find some way to partial fractions this. Does anyone know or remember from calculus how this partial fractions? What's the general partial fractions thing if your denominator has 1 minus 7z cubed and like 1 plus 5z to the first power? Raiden, you're right. If you get 7, 7, 7, you win the slots. That is true. So you see, 7's a great choice. Does anyone know what to do with this kind of partial fractions thing? This is from calculus. Zhejia?
I mean, in general, you would have one fraction with just 1 minus 7z, and then another partial fraction with 1 minus 7z squared, and then another one with 1 minus 7z cubed.
Good. So what I'm going to do is I'm going to say, I'm not going to spend the time to prove why you can do this, because in calculus you didn't either, and this would take me even farther afield in the class, which I would actually normally love to do, but we just don't have time. This semester is a bit too short. But I'm going to say, because in calculus you did this sort of thing, we'll do it again. Is that okay? In calculus, did you do this sort of thing, where you got like a certain power, and therefore you go with like the linear term, the second term, and all the way until that power? Let's just use that. We'll say we believed it in calculus, we'll believe it now. If you want to know really why this is possible, the best way to prove it is actually back to linear algebra. If you haven't gotten the point by now, I'm trying to emphasize that linear algebra is probably one of the most useful math classes that you will take in college. I strongly believe this. It is the foundation for all kinds of stuff. But anyway, so you do something like this. And the important thing is this partial fractions thing. All of these blobs, there's no z's in them. There's no n's in them. In fact, there's no n in anything I wrote here. I just have some function. There's no n here. It's just like some rational function. And so now I've gotten this piece. Okay, so if I have this, you could perhaps try to solve for the blobs, but more importantly is, what's the deal with these power series? So I already know something about how to get the power series of 1 over 1 minus 7z. That one's the geometric series. Okay, I'm going to write a few annotations. So this thing comes from just plain geometric series. And if you remember, what we did for the second one is we took the derivative of the geometric series. Because it's like, well, it wasn't that bad. If I've got this thing, I can take the derivative of it. So this was the derivative of the geometric series. Anyone have any ideas for how to get that one? We're going to actually do this one in like 3 ways, because it's just fun. There's like multiple different ways to try to solve this thing. So how might I try to get that? Second derivative is saying, yes, thank you. Second derivative, why not? Because that's exactly what happens. If you take derivatives, all that happens is you keep kicking out like these, keep kicking these like 7s into the front. But this is like second derivative. Okay, now that I'm talking about this, let's try to do this in general. And yes, there's oh, you could also, actually, Sean, you're right. You could also multiply the first two. I said we're doing this in 3 ways. So the second derivative is one of the ways. The multiply the first two is related to another one of the ways. All right? But now we're going to talk about this. Let's do this not with 7, but with a lambda. I know that I say 7 is my general thing, but now I want to see what happens as I go carry a lambda around. If you did it with 7, you'd also notice, because 7 is sufficiently prime. I mean, it is prime, so that you just notice when you're multiplying things or not. All right? So what do I know? I know that 1 over 1 minus lambda z. Lambda is my 7. Okay, 1 over 1 minus lambda z. That's equal to 1 plus lambda z plus lambda squared z squared plus lambda cubed z cubed, that's a cubed, plus dot dot dot. Okay, well, if that's the case, let's go in derivative at once. So if I take a derivative, then on the left, I get minus 1 over 1 minus lambda z squared times a minus lambda. Okay, and on the right, what do I get? I get derivatives of stuff. So I just get the lambda plus, this is what we did last time actually, 2 lambda squared z plus 3 lambda cubed z squared plus 4 lambda fourth z cubed plus dot dot dot. Okay, but I actually wanted a clean 1 over 1 minus lambda z squared. Okay. Fortunately, 2 negatives make a positive, so I don't have to worry about the sign. It's just like positive. But I have to divide out the lambda. So I divide out the lambda, and I get 1 plus 2 lambda z plus 3 lambda squared z squared plus 4 lambda cubed z cubed plus dot dot dot. Okay, now we do it again. If we do it again, I have to take another derivative. Okay, if I take another derivative, my left-hand side, it's going to get an extra factor of 2 now. So it's like minus 2 over 1 minus lambda z, now it's cubed, and there's a times minus lambda for the chain rule, equals, and I take more derivatives. So if I take a derivative of this, can someone help me say what this is? I don't want to be the one who does everything. Someone help me get through all of these terms. Just raise a hand. Then it's more fun than just me talking. We're also going to look for patterns as we do this. Braden.
The first term is going to be 2 lambda. The next one should be 6 lambda.
Yes. Okay.
And then 12 lambda cubed times z squared.
And so on.
It kind of looks like that we're dealing with permutations here.
Yeah, it looks sort of like permutations. Looks like we're multiplying stuff together. Can you help me out with the prime factorization? Like when I say prime fact, I actually don't want to do prime factorization. What did we actually do to get the 6?
We did 2 times 3, isn't it?
2 times 3. And what did we do to get the 12? Oh.
3 times 4.
Interesting. And now what do we need to do? We need to get this clean, right? I don't like this minus 2 over stuff, right? So what I need to do is I need to divide by a 2, and I need to divide by a lambda, because 2 negatives make a positive. So if I do that division, I get a straight up 1 over 1 minus lambda z whole thing cubed, that's a 3, is equal to, now it's going to be, I'm going to do it in a funny way. I'll say 2 over 2. The lambda is gone, because I divided by a lambda. Then I get, you said it was 2 times 3 over 2. Actually, can I flip them? I want to call it 3 times 2, just for fun. 3 times 2 over 2, I have a lambda z, plus a 4 times 3 over 2, lambda squared z squared, because I divided by a lambda, plus the next one's obviously going to be 5 times 4 over 2, lambda cubed z cubed. Oops. Okay, what do these look like? Have you seen these things before? Venkatesh.
Just like the thing choose 2.
Yeah, it's like the thing choose 2. That's kind of cute. So we got some stuff choose 2s. That's interesting. So I'm just saying what's going on here is that's a 4 choose 2. I just felt like calling that out. We'll notice more and more patterns as we keep going. Now, that's how you get this 1 minus lambda times z cubed. Well, sorry, 1 over 1 minus lambda z all cubed. You get something that looks like this. Just for fun, even though the problem didn't ask me to do to the 4th power, what would it end up looking like if I did the 4th power? I think the easiest way for me to do that is I'm going to attempt to copy this yellow thing onto the top of the next screen. Okay? So what we had was 1 over 1 minus lambda z all cubed, and that was equal to, it was a 2 over 2, which was actually a 2 times 1 over 2, plus a 3 times 2 over 2, that was times lambda z, plus a 4 times 3 over 2, lambda squared z squared, plus dot dot dot. Derivative again. I just want to show how this is interesting. Derivative. What are you going to get? Well, you're going to get something where there's a minus 3. There's a 3 because it's a cube, right? So it's minus 3 over 1 minus lambda z to power 4 times the minus lambda by chain rule equals, you drop the first thing, because there's no z to derivative. And then so I get the 3 times 2 times 1 over 2 times just a plain lambda, plus a 4 times 3 times 2 over 2 lambda squared z, plus I guess the next one will be 5 times 4 times 3 all over 2 lambda cubed z squared. What's happening? What will happen next? What's my next thing I do? Someone help me out. Abby.
Then you're going to want to do the same thing again, where you divide by 3 and divide by your extra lambda.
Good. So this is to the 4th. Divide by 3, divide by extra lambda. And what does it end up looking like? Well, let's just do it. So if I divide by 3 and divide by the extra lambda, look what happens. 3 times 2 times 1 over, well, there's a 3. And you know what? It's also 3 times 2 times 1. That's actually kind of nice. Times 1 is the same thing as not writing the times 1. Plus, I get a 4 times 3 times 2 all over, I'm tired of this. I'm just going to call it 3 factorial. Lambda z plus 5 times 4 times 3 all over 3 factorial lambda squared z squared. And what you see here, what are these? Choose 3s. Yes, these are all choose 3s. So for example, this guy here happens to be 5 choose 3. I want to focus on that just for fun. This is 5 choose 3, and it's going to be times, lambda squared z squared. All right. So I've just found out that the coefficient of, say, z to the power something. Let's get a formula then. Because I just did this for the 4th power, okay? Let's actually write down a formula for, in this thing, the coefficient of z to the power n is equal to what? Can anyone help translate this? Like, we found the pattern, and that's enough for me. It's like it works all the way to 4. By induction, it should be able to be solved for all of them as I keep going. But what is that general term? It'll be something choose 3. But what? Venkatesh.
Is it m plus 3?
I hope so. So it'll be n plus 3 choose 3. When I say I hope so, I mean that's what I see. And I hope that's right. Okay, n plus 3 choose 3. That's cute. N plus 3 choose 3. Hey, have we seen anything else in the counting section of this course where we might have had things like n choose 3 choose 3? Well, that was when we were counting paths. Can anyone think of anywhere else in this course where we have seen a choose come up as the number of ways to do something? Sean.
Binomial theorem.
Binomial theorem is one. Let's do brainstorming with a fast association. Binomial theorem. What else? Where else have we ever seen a choose come up as the answer? Aaron. Stars and bars also comes up, okay? Let's think about the stars and bars here. What's the stars and bars of n plus 3 choose 3? What is that? That also happens to be some stars and bars thing. Stars and bars. Can anyone tell me what that's counting if I think about stars and bars going on? N plus 3 choose 3. Like, how many stars, how many bars, what am I actually trying to do? I want to say that's the same as counting the number of ways to do something. When do you do n plus 3 choose 3? Abby?
You could say that you have like n stars and then, sorry, 3 bars that you're trying to pick.
Okay, so I have, good, n stars and 3 bars. Well, when I needs to be more legible because it's exciting. Okay, n stars and 3 bars. If you have 3 bars, how many things? So you're like dividing n stuff, right? You're distributing n things to people, okay? And if you have 3 bars, how many people are you distributing to? It's not 3. It's 4, okay? So this is good. N stars and 3 bars was the correct answer to how many stars and how many bars. But the 3 bars, what that means is 4 people. N things distributing to 4 people. What does that have to do with 1 over 1 minus lambda z to the 4th? Let's write that down again. If I had this and it was blue, 1 over 1 minus lambda z all to the 4th power. Well, now let's use something that somebody else suggested, which is like, hey, you could just multiply some stuff together, right? And so this happens to be 1 over 1 minus lambda z times 1 over 1 minus lambda z times 1 over 1 minus lambda z times 1 over 1 minus lambda z. That is true. Well, now each of those is an infinite geometric series. So that means it is a 1 plus lambda z plus a lambda squared z squared plus a lambda cubed z cubed plus dot dot dot. I got 4 of them all smashed together times 1 plus lambda z plus, I'm going to write dot 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 because they're all the same. I'm getting more lazy, so I'll say 1 plus dot dot dot, 1 plus dot dot dot. Okay, is there a good reason why the coefficient of z to the n just so happens to be the number of ways to distribute, that was supposed to say distribute n stuff, coins, call them coins, n coins among 4 people, and that thing times lambda to the power n. Why would that be? Because that's what we just found out. We just found out it was n plus 3 choose 3. Oh, did I forget to write the... Oh no, there's a lambda to the n on the previous screen that was missing the whole time. Times lambda to the n. Sorry about that. There was supposed to be a lambda to the n here. And so over here I have the lambda to the n also. What does this thing have to do with distributing? Venkatesh.
It's like you're choosing some like powers from each of the 4 things, and then like those sum up to n. So it's like you're taking each some amount of power from the first one, the second one, the third one, the fourth one.
Yes, it's the same as the proof of the binomial theorem. In the binomial theorem, if I want to know how do I get a z to the power n, well, I need to go and pick some number of, like some power of z from each of the 4 things. Okay, the lambda thing, why is there a lambda? It's just because all the z's come with lambdas. It's like, if you got a z, you got some lambdas. They all come in a package. You cannot get z's on their own, right? They're all like, lambda and z have the same like power of each other all the time. So it's like, buy a z, get a lambda free, something like that. And you also can't get rid of it. But so the point is, if I have n things, I want to make a z to the power n, so I just need to know how many ways could I possibly distribute to decide which power of z do I take from each of the 4 things. That's why. So I'll write, since you get, I'll call it a lambda to the n, well, I'll call it lambda z, parentheses, to the power n, total, divvied up among 4 factors. Does that sort of make sense? Like, that's really what's going on. I've got these 4 factors, and every single way of deciding, I want to take the third one, or I want to take lambda z raised to third power from here, I want to take raised to the 1 power from here, I want to take raised for whatever power from here, and the sum of the powers that I pick has to exactly match n, because that's my goal. Okay, so what we have just found out is that this is another way of finding out that the coefficient of z to the power n happens to be this n plus 3 choose 3. So what have we found out? We've found out that the coefficient of z to the power n in this power 4 thing is n plus 3 choose 3. Well, that just shows that in general, if we were to actually prove this by induction, in general, so we found 2 ways to get to this, by the way. One way to get to it is just like directly right here. It's the stars and bars. The other way was like, oh, let's go and do something and find a pattern. But in general, what I'd find is that 1 over 1 minus lambda z to any power, let's call the power r, that has the coefficient of z to the power n equal to, well, it's going to be the number of ways to split n coins among r people is the stars and bars. N plus r minus 1, choose r minus 1, times lambda to the power n. Is everyone okay with that? We've just done this in 2 ways. I actually promised you a third way. I'm looking at the time to decide if I can do this. Yeah, let's do a third way real quick. There's a third way to get this power as well. And the third way is called, hey, let's take some derivatives for fun. Let's actually go and differentiate this thing. Let's go and take a whole bunch of straight up derivatives of this thing to get the power series. Because actually the power series of this maybe is not that bad after all, if I try to take derivatives of this. I said it was scary, I didn't want to do it before. But you can actually try to do this and just use Taylor's theorem. What would happen? Or another way is just to like use Taylor series on let's give this a name, g of z. I actually want to write it like this, 1 over 1, I'll call it actually 1 plus z, so 1 plus, let's use minus, 1 over 1 minus z to the power r. Okay, I just want to say, I claim this is actually not bad. We can write down the Taylor series for this, and r is like some number. And in this problem that we were looking at, r could be like 4 or something like that. Okay, what does Taylor series tell you? Well, I've got to start taking tons of things like the evaluation at 0 and the derivatives at 0. So let's start. What is g of 0? Well, let me write a table, okay? So I'll write g is equal to 1 over 1 minus z to the power r, and I'll say at 0, let's draw it underneath. At z equals 0, what I get just plugging in 0 is 1. That was the easiest one. Now what happens if I take g prime? What's this? Braden.
You typically just end up multiplying your fraction by r and then increasing the exponent plus 1.
Okay. So I take it you guys have taken enough calculus classes in your life to not need me to write the minus thing. The minus thing is just for me because I'm slower. But it's basically like minus this thing over the power r plus 1, and then there's also an r that sticks up on top, and you chain rule with a minus sign. But if I go and do this, and at z equals 0, actually that's not that painful, is it? What is this? At z equals 0, I can do that. That's just r. What's the next one? G double prime. Can anyone tell me what happens if I take another derivative? And you'll see interesting things happening. What's the next derivative? Well, I'll go ahead and do it. So it's like, you know, it's going to have, oh yeah, Jack, go.
Yeah, hope we don't mess this up, but I think we get another factor of r plus 1 in the top.
Yes, you do.
The r.
And the
then
bottom?
The bottom 1 minus z to the r plus 2, and okay.
Yep. At z equals 0, r times r plus 1. Okay. Does this make you happy to see this sort of stuff? This is actually very good. The reason this is very good is, what's the Taylor's theorem supposed to tell you anyway? The coefficients of the power series, I should take these things and divide them by some factorials. Doesn't this look familiar? These are like exactly what we were just talking about. These are the whole things coming back again. So the next one was g triple prime. If I just write that to get the pattern, r times r plus 1 times r plus 2 over, it's 1 minus z to the power r plus 3, which, the same arrow thing, will give you r plus 1, r plus 2. Terrific. Because actually what I'm going to do is I'm going to care about the actual coefficients in the Taylor series, so I'm going to divide them by the factorials. So if I want to know the coefficients in the Taylor series, we just divide by various factorials. So this will just be 1. This will be r over 1. Let me try to do it where I won't run into myself. This will be like 1. This will be like r over 1. This will be like r times r plus 1 all over 2, right? Because it's 2 factorial. That's what I do. And the next one is going to be r, oops, wrong color. r plus 1, r plus 2 all over 3 factorial. Okay, so what I'm finding out is that I'm getting the same form again. Like the form I'm getting again is always going to be these like bunches of r's multiplied together, divided by, whatever factorial I have. Okay, so when I've gotten all of this, now I actually have a thorough understanding of what are going to be the coefficients. We've gotten 3 different ways of getting these like things choose 3. Who cares? Let's now put everything together. So when I have all of these different things here, I've just found out that, I've got these coefficients. And the coefficients are all of the form, like n blah, 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 choose r minus 1. Okay. If I went back to look at the problem that I had with it, which had this 7 inside it, where was the 7? Yeah. So I have this 7 here. Let's think about what things are fixed and what things are the r's. The r is the 3 here. Okay? And what I'm going to end up having, I just want to remind people that r is like something like the 3, and the lambda is something like the 7. So when I'm over here, I start to find out that the coefficient of my nth term is going to be like n plus 3 choose 3, or n plus 2 choose 2 times this lambda thing. How is that useful? So if I go back to this original thing, which had the 7 inside it, I'm finding out that so now we're here. Let's go to some concrete numbers and we'll see the pattern that comes out. If I'm over here, I found out that the coefficient of my nth term from, let's say, the yellow thing, over here, coefficient of z to the power n, sorry, not nth term, that's equal to something like n plus 2 choose 2 times lambda, well, that is a lambda here, lambda to the n. Okay, so what do I know now? I know that that's what I get out of the yellow. Out of the yellow, I'll get like n plus 2 choose 2 times this lambda to the n. I was previously lucky that I could write blob times lambda to the n. I can't anymore because this n plus 2 choose 2 has an n inside it. But what I'm going to say is that this n plus 2 choose 2 is not really a blob, but it's a polynomial in n. Well, let me write this way. It's a degree 2 polynomial in n. Degree less than or equal to 2, polynomial in n times lambda to the power n. Are people okay with that? Because if I wanted to do this n plus 2 choose 2, we've seen it. It's going to be, you expand it, n plus 2 times n plus 1 divided by 2, blah, 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 blah. And you get this like degree 2 polynomial in n times lambda to the n. The reason I did that is because from the green side, there's a way to express what is the coefficient of the z to the n in the green thing. What is that if I was going to use this same type of language? In the yellow one, I said it's a degree 2 polynomial in n. How about here? Braden?
It's some linear expression in N.
It's a degree 1 polynomial in N. Okay, so this guy here gives me the coefficient of z to the n is equal to degree, it's actually a degree 1, but I'll just say less than or equal to 1 polynomial in n times lambda to the n. Well, how about the white thing? Well, the white thing is a degree 0 polynomial. It's just like constant. A degree 0 polynomial in n times lambda to the n. Coefficient of z to the n is equal to a degree less than or equal to 0 polynomial in n times lambda to the power n. Why did I do that? I did that because I'm supposed to add the three together. Remember, what I actually have to deal with is I have blob over 1 minus lambda z plus blob over 1 minus the lambda z and that thing squared plus another blob over 1 minus lambda z and the whole thing cubed. So what's actually happening is I'll have a lambda to the power n in my coefficient of z to the n, but I'm going to combine together lambda to the n times a degree less than or equal to 0 polynomial plus lambda to the n times a degree less than or equal to 1 polynomial plus a lambda n times a degree less than or equal to 2 polynomial. What happens when I add a degree less than or equal to 1 polynomial with a degree less than or equal to 0 polynomial with degree less than or equal to 1 polynomial plus degree less than or equal to 2 polynomial? Well, if I only know that they're blobs, I don't actually know what the coefficients are. All I know is that in the end, when I add all this together, I just will get some degree less than or equal to 2 polynomial that I built out of 3 polynomials whose degrees are all less than or equal to 2. So we'll continue, we'll give this more detail next time because it's a very important point. But I just want to say, when I go back to this thing, what I end up finding is that I end up finding that if I take all this thing, then the coefficient of z to the power n is equal to some polynomial of degree less than or equal to 2 in n times lambda to the power n. Sorry, not lambda. I have numbers now. That's a 7. 7 to the power n plus a blob times negative 5 to the n. That's what that punchline is of what we have just done. Because what ends up happening from this thing of the 1 over 1 minus 7z, 1 over the square of that, 1 over the cube of that, I just get like some random blobs that go in front of n's constants or n squareds. And all of those are hit against the same 7 to the n. And then there's this other guy over here, this 1 over 1 plus 5z. That's a plain old geometric series. Those are the easy ones. That's just like minus 5 to the power n times a blob. Oh, look at that. There's 4 unknowns. That's the general form of a solution of a 4-term recurrence. This was a 4-term recurrence which has this like A, B, C, D. The way you solve it is you go and factorize, or if you know the solution of how to find the roots of that characteristic polynomial, those roots with the repeats will tell you how high of a degree of a polynomial to use. And suddenly this holds for every n. So I just go and plug in n equals 0, 1, 2, 3, and I solve a system of 4 equations and 4 unknowns. And I'll find out what are these 4 constants. Okay, so that's how the general form of this theorem works. I'll mention some more things about that next time. There's a holiday on Friday, if I understand correctly. Is that right? Mid-semester break. So next time is going to be Monday of next week. And yeah, we'll continue from here. But you have now seen like the general way you solve these homogeneous linear recurrences. Uh-oh, we have an exam on